Okay, now we continue with 74 times 85 device. Okay, you can at page 1 to 6 of the module. Okay, so 74 times 85 integrated circuit is a device that compare 4-bit values. Okay, means its limitation is 4 bits. So if we want to have if you want to use this for 8-bit or more, we need to cascade the device. Okay, we need to use multiple chip of 74 times 85 if we want to have more than 4 bits of inputs connections. Okay, so this one is meant for 4 bits. Okay, but of course we can cascade it if you want to build a bigger chip having more than 4 bit inputs. Okay, okay, what 7485 device do is that, okay, it has two 4-bit input. Okay, means it have two 4-bit, means you can have two 4-bit input. Mean first you can have A3, A2, A1 and A0 as your first 4-bit input, and second you will have another one, let's say B3, B2, B1, B0, okay, as the second 4-bit input. Okay, so and three outputs, which is A greater than B, A equals to B, and A less than B. Okay, furthermore, it has three additional inputs, which is IA, B, IAA, IA equals to AB, and I less than B. Okay, so which allow cascading of multiple 74. This allow us to compare 8-bit, 12-bit, and so on. Okay, if we want to have more, if you want to have bigger comparison. Okay, for example, if you want to have to compare 8-bit, 12-bit, and so on. So this is the standard 74 times 85 comparator device. So you can see you have a first 4-bit input and second 4-bit input. This one is your 3 additional inputs, and this one is your output. Okay, which will deduce whether A is less than B, A greater than B, or A less than B, A equals to B, and A greater than B. Okay, so here, if you want, for example, if you want to cascade, okay, 274 85 device in order for us to compare 8-bit values. Okay, so you can see this one we compare for the first nibble. Okay, nibble is the 4-bit, and this one we compare the upper nibble 4 bits. So this combined with this, you will have 8-bit. Okay, so compare. So what you can do is actually you cascade the device. Okay, so let's we go to the operations of the device. Okay, how we actually going to understand its operation. Okay, let we take the 74 times 85 device or chip, whatever you may call it. Okay, so first you have the 3 additional inputs, okay, denoted as I is less than B, I A equals to B, and I A greater than B. Okay, then you will have you will have 2 4-bit inputs. Okay, I hope you guys able to listen to my voice clearly, because I know there is a vehicle sound outside. Okay, so let's continue. Okay, so we have this one, we create, let's say this was this input A, and the second is our input B. Okay, and then we have the 4-bit combination. Okay, and then we have another for the similar B3, B2, B1 and B0. Okay, so let's say we just take the same designation. We just put this one is A3, A2, A1, A0. Okay, and this one B3, B2, B1, B0. Okay, if you see, this one is consists of 4 bits and this one is also consists of 4 bits. So this one you can create, let's say if you want to create 8 bits and so on. So this one will be, if you want to create 8 bit, this one will be the lower nibble, this one will be upper nibble. Okay, so this one is actually just a nibble because it's a 4 bits. This one also the same, is a nibble. Okay, then we have output, 3 outputs. Okay, our output can be A greater than B, A less than B, A equals to B, and A greater than B. Okay, now in order for us to able to compare this input, okay, we must set the connection for this additional input with this state. Okay, this one must be set to 0, this one must be set to 1, and this one must be set to 0. Okay, in order for us to enable the function, this one we have to use this combination so that we able to compare 4-bit number. Okay, so what happen if we choose different numbers? Okay, okay, let's say for example, let's say if we chose different value now. Let's say if this one is set to 1, okay, or this one is set to 1, for example. Okay, either this one or this one, for example, because this is meant to be 0. Okay, this, both of them is meant to be 0 in order for us to perform the comparison operation. Let's say if this one is set to 1, what will be happen? Okay, if this one is set to 1, what happen is that this one, the output of A less than B, okay, A less than B will be set as 1. Okay, if we choose other value, okay, because this is meant to be the value for it to perform the comparison of 4-bit input. Okay, what happen if we set this one is equals to 1? Okay, similarly our output will always become 1. Okay, without checking the A and B input. Okay, so which is wrong. Okay, so in order for it to be able to do the comparison operation, make sure that this one is 0, this is 1, and this one is 0. Sorry, I think there is sorry, I need to check first on the lighting. It's like it's blinking. Okay, so now it's okay. Sorry for the interruption. Okay, and then what if happen is that the outputs are not defined if more than one of the cascade input are high at the same time. Okay, okay, the output are not defined if more than one of the cascade input are high at the same time. Let's say if you have 1, 1, 1, okay, then the output will be undefined. Okay, are not defined because all of them are high. So this one you need to make sure this is the combination for your input. In order for this 74 times 85 to perform the comparison of the two 4-bit input. Okay, now the cascade enable more than one device to be connected. Okay, for example, as in this figure, you can see, right? So we just simply connect this output to the next input of the upper nibble. Okay, this one, it will enable it to compare for 8-bit combinational inputs. Okay, okay, now let's we see from the truth table. Okay, from the function table, sorry. Okay, now let we consider the 74 times 85 comparator function table. Okay, so you see there is a lot of combination because you can have a lot of possible combinational inputs. Okay, so let me go for the first row. Okay, for the first row, so it compare A3 until A0 with B3 until B0. Am I correct? Okay, so let's say, okay, at the most significant bits, okay, we have found that A3 is actually greater than B3. Okay, so if this condition is true, then there is no need to compare for the next least significant bits. Okay, because this one already determined whether this combinational input of A is lesser or greater than B. In this case, is greater. So we will have the don't care condition for expression inputs. Okay, so IAB or I greater than B. So the output, okay, corresponding will be high for A greater than B and low for A less than B or A equals to B, because the number A combinations is actually higher, greater than the B. Okay, next we go for this one. What if A3 now less than B3? Okay, for example, okay, okay, if you see this, you can see that B3 is actually greater than the A3. Am I correct? So in this case, the same, no need to compare for the least significant bits, the next least significant bit, because here we already know is actually B3 is greater than A3, which is A3 less than B3. So that's why output here is set high and the rest are set as low. Okay, next, okay, what if we have A3 and B3 having the same number? For example, okay, okay, having the same number at the third weight. Okay, so we will see the next one. So here you can see actually A2 is greater than B2. Okay, so if we have already able to determine this situation, so those no need to compare for the next two bits, then we can quickly jump there. We know that A is greater than B, is high, set to high for the output, and this one is set to low. Okay, similarly for this one. Okay, you may use the same concept. Okay, the next, if we have A3 and B3 are the same, A2, B2 are the same numbers, so we will move to the next, which is the second least significant bit. Then we found that actually A1 is greater than B1, so you set this one as high because we know A greater than 1, A greater than B. This one is set to low. Okay, similarly for this case, if they are the same for the third, for the most significant bit, and for the second most significant bit, we will compare the third significant bit. Then we found that A1 is less than B, so it is set to high for A less than B. Okay, similarly the same for these two conditions. Okay, you guys can try yourself. Okay, next next, what if we have A3 equals to B3, A2 equals to B2, A1 equals to B1, A0 equals to B0. Okay, what happened? Okay, and then if you see, there is three conditions. Okay, there is three conditions here where we actually have the same number. Okay, this means that A, B, okay, means that let me make into this so that you understand. Let's say they are the same number. Okay, okay, for this condition they are the same number. For example, I sign, I have to re-record again because my phone complains of memory. Okay, in fact it's almost full. So where the video stuck just now is until 111. Okay, so let's say I don't want to delay so much in explaining because I'm worried it will stop again abruptly. So let's say you have A, B having the same combinational input. So this one is the case where we have A and B are the same. This one is just assume of assignation. Okay, you can put any numbers as long as they are the same. This one I just choose 111. Okay, so then if we set IAB equals to high here, this one is low, following these situations. Okay, so it will perform the comparator function, and it will show that AB will be, output AB is high because this number are equals. Okay, what if we have IAB set to high? Okay, we know that I less than B, okay, I less than B shouldn't be set to high. So if this is the case, then your corresponding output A less than B will always set to high and other will be low, regardless of whatever input combination that you have. Okay, how about if we have IAB greater than 1, means IAB is high, this one. Okay, this one. Okay, for example, so we will have this one, output will be set to high and others are low for corresponding A greater than B. What if we have okay, this situation now? Okay, the same combination of inputs. Okay, let's say we set IAB is high. Okay, then we will able to see that output A greater than B is high and this one will be set to low. What happen if we have more than one output, more than one input is set to high? Okay, here, because you say the outputs are not defined if more than one of the cascade input are high at the same time. Okay, so we cannot have more than one input to be set as high. So if this is happening, then all will be set to low. Okay, and likewise, if there is none set to high, okay, which all are low, then we will have this output to be high and this one is to be low. Okay, try to understand this one by yourself. Inshallah, I believe you can. Okay, so we go to the next. Okay, which is the 74 times 280 device. Okay, so we go for 74 times 280 device. Okay, this one is actually parity generator or checker. Okay, shown in figure 10.15. Okay, so it's an MS chip that can operate either as generator or checker. It's a function table shown in table 10.3 here. Okay, the device has 9 inputs A to I, A, B, C, D, E, F, G, H, I, and 2 output, or whether it's sum of even or sum of odd. Okay, output even if one is the if the number of high input is 1. Okay, if you have a even number of high input, then we set even as 1. Okay, and likewise, output odd will become 1 if the number of high input is odd. Okay, so depends on the number of the inputs. Okay, now to use as a parity check generator, okay, to use as a parity generator, you know, right, parity, we have parity, odd parity or even parity. Okay, use add input for data and ground one inputs. Okay, you see we have 1 2 3 4 5 6 7 8 9. Okay, so we use add input and the other one output will ground. We don't care which one, but at least one of them will be grounded. Okay, you can ground here, you can ground here, for example. Okay, but let's say just for simplicity, okay, make easier, we just ground this one. Okay, the choice of input to ground is not important, just like what I said. For transmission with odd parity, we use the output even as the parity bit. Okay, if we want to transmit odd parity, okay, we use output even as the parity bit and append it with the original data bit. Okay, if we want to transmit odd bit, so this will make the number of 1 in data and parity become odd. Okay, at the receiver, all 9 bits become input to A to I. Okay, because we will have this one at the this one at the receiver. Okay, now at the receiver, all 9 bits become inputs to A to I. Here the output even is 0 if there is no alteration in data, and 1 if A bits get changed. Okay, to use for data transmission with even parity. Okay, this one later on. Okay, let's say if we want to send for the odd parity. Okay, if you want to send for transmit with odd parity. Okay, okay, never mind, I just continue. I guess later we discuss this table. Okay, to use for data transmission with even parity, we use odd for the parity bit to send, and also for the error indicator at the receiver. Okay, so figure 10.16 show how the device may connected to detect errors in the transmission and data bit. Okay, this one is to check how we're going to check the errors. Okay, you guys can, I think this one is quite straightforward. Okay, now, okay, so if we want to if we have number of high input is even, okay, even, and if we set this one as 1, okay, okay, even plus 1, then what we have? Okay, then we will have a transmission with an odd parity. Okay, and if we want to use for data transmission with even parity, we use odd for the parity bit to send. Okay, here is odd if you want to send data with even parity. Okay, so if you can see, if your number of high inputs is even, then your output here will be 1 and this one will be 0. Okay, and if your number of high input is odd here, then you will have an odd function here. Okay, output at odd. So let me see. Okay, this one is quite straightforward. Okay, you see, this is your transmitter. Okay, your TX, and this one is your receiver. Okay, so you can see this is your parity generator. Okay, and you have parity checker. Okay, so you see A7, B7, A6 corresponding. Okay, code word. Okay, this is data word, this is code word, and the syndrome. Okay, this I think you guys have learned in the previous lecture or slide. Okay, about syndrome. Okay, what is the syndrome? So please refer to the previous lecture. Okay, thank you very much. See you in the next class. Okay.